My name is Liang from the Hong Kong Polytechnic University. It's my pleasure to introduce our recent work. The title is Making Sense of Mechanical Vibration Period with Sub-Millisecond Accuracy Use Backscatter Signals. Today I'm talking about the vibration. In fact, people are subject to the vibration every day. For example, when you put your smartphone into the silent mode, its vibration alerts you to the new message. Any sound you hear is the result of something somewhere vibrating. And the vibration also causes some serious problems with regards to your health, the structural damage, and the noise issues. I can give you numerous examples to show how important to measure or monitor the vibration. Here, I give the 3 examples. For example, the centrifugation is a process that separates a mixture into different layers. It is a necessary phase before we do the blood testing in the hospital, and it is also the difficult and tough task to manage thousands of the magnifications of blood testing in the hospital. And the most common and bothersome auto problems is the vibration. Maybe you ask yourself, what does it mean if my car is vibrating? And each bridge and building has a fundamental frequency at which it vibrates. The fundamental frequency indicates how this architecture responds to the forces, like the winds or earthquake. It's important to measurement the fundamental frequencies of architecture. Vibration is a mechanical phenomenon. It's complex to quantify the characteristics of the vibration. However, we can consider a vibration from its basic parameters, the acceleration, velocity, or displacement, or the amplitude. The traditional approach for vibration sensors, vibration sensing requires special sensors. For example, we can attach accelerator to the vibrating surface of the rotating machine for the diagnosis. Or we can use the laser meter to measure the speed of the spinning. However, this method has many drawbacks. We turn our attention into the mature technology RFID, which is evolving as the main technology for the identification and tracking. In this work, we supplement on RFID backscatter communications with a fine-grained sensing function. In contrast with the past approach, the RFID-based solutions offers many appealing features. For example, its cost effect. It can be used in the non-line of the sight scenarios. And moreover, the RFID tag contains the ID. We can easily to associate each vibration with the object. Totally, in this paper, we make the following contributions. First, we propose the RFID-based system for sensing mechanical vibration with sub-millisecond accuracy. Second, in this paper, we design a group of signal processing algorithms to address the negative impacts. And we also implement a prototype using the Quartist RFID systems. We have submitted the benchmark and also scaled into the GitHub. You can download it for free. Our idea is very simple. We attach RFID on the vibrating surface. The vibration displaces the tag within a small range and results the regular change of the backscatter signals. We can achieve the vibration context, like the frequency or period, by designing such pattern. To show how our vibration signal looks like, I performed an experiment. I attached an RFID tag on a turntable and let it spin at the frequency of the 2.8 Hertz. And this figure shows our phase frequencies. Of course, namely, it's our vibration signal. We can see that our vibration signal is discrete and the periodical. And more important, of the tag as one sampling of the vibration. Sampling is a process that converts a continuous fundamental theory about the sampling is next to the sampling theory. It states that the sampling frequency must be twice greater than the maximum frequency of the signal. and then you can exactly recover the signal. And nowadays, a commercial RFID reader can read the text for 40 times per second, offering the sampling frequency of the 40 Hz. According to the Nyquist sampling, we can only monitor the vibration with a frequency lower than the 20 Hz. Apparently, it's insufficient for most of the cases in our daily lives. And the recent advantage in the field of comprehensive sensing has developed a reliable recovery algorithm for sparse signals. And inspired by the CS, we attempt to recover the vibration signals with a low read rate, and we call this process as the comprehensive reading. However, we face the two challenges. The first challenge is that CS requires the signal very sparse. However, our time demand vibration signals is not qualified. And second, the CS makes a measurement matrix in advance and then schedule the sampling based on this matrix. We use a quotist RFID, which means that we cannot make any modifications to the reader, and we cannot command the reader to reply at a specific timing. To address these issues, we have two observations. The first observation is that, as I had mentioned, the vibration signal is a periodic signal. Any periodic signal can be expanded as a combination of a series of harmonic frequencies. So our vibration signal is compact and sparse in the frequency domain. The second observation is that the commercial reader uses the Aloha-like protocol to avoid for the anti-collision. Specifically, the readers divided the time into different time slots and allowed the tag to randomly pick up a time slot to backschedule its ID. At a high level, we can see that the tag is randomly read. And such fashion offers an inherent random sampling in our case, in our scenarios. How to use this inherent? In order to use this inherent random sampling, we construct a measurement matrix like this. We further group the time slot into different frames, and each frame corresponding to each row in our matrix maker. Measurement matrix, sorry. And lastly, we put all the pieces together. First, this figure shows the basic ideas of the comprehensive reading. First, we project and recover the vibration signals in the frequency domain. And we also construct a measurement matrix after the readings. Okay, our approach is different from the past CS-based systems for 2 points. The first is that we make the measurement matrix after reading instead of in advance. And the second is that the trend in the past CS-based system, the sensing result is naturally got by the overlapped signals over the medium. However, in our case, we manually aggregate the phase values within a frame into a sensing result. This slide gives an example the recovery of the vibration signal using the comprehensive reading. We can see that the signal is sampled lower than 3 times in each cycle on average. And however, its recovery of the signal is almost as the same as the ground truth. You may ask the question, can we inspect the frequency varying vibration? The answer is yes. We can achieve the continuous spectrum by sliding a Gaussian window over the samples under a practical assumption that only one fundamental frequency dominates the vibrations during the short measurement time. Okay, And the up to top picture shows the samples, which is undersampled, and the bottom picture shows the spectrum we have obtained, and we can see that this shape is well fit our operations. And we also address two other issues in our paper. And the first is we address how to magnify the subtle vibration signals. And the second is we design an enhanced RF folding to faster find out the vibration period. We implement our prototype purely based on the latest RFID devices. We use the impinge reader, island tag, and we also use the standard protocol to communicate with the reader. This figure shows our experiment setup. We use 10able for our benchmark because two reasons. The first reason is that majority of the vibrations are caused by the spinning of the rotating machine. And the second reason is it's very easy to get the ground truth of the spinning. We use a laser reader to get the ground truth. And we have a short video to show our benchmark. And we also have the demo. You can welcome to visit our booth to visit our exhibition. Firstly, we adjust a very low frequency, and we can see that the recovered vibration signal, and then we increase the frequency to the maximum. And from the video, we can see that it almost undersampled even use the camera. And this is a recovered vibration signal. And we also conduct another case study we will introduce it later to monitor the centrifugation. And we attach RFID on the tube, on the blood tube, and let it spinning at the centrifugation machine with the frequency of the 2000 RPM. And this is a recovered signal of the centrifugation. Okay, here I only present two evaluation results. The first is we represent the period accuracy with a different RPM. RPM is another frequency unit used in the mechanical areas. We randomly select 8 RPMs and identify its period accuracy. We can see that the mean error is under the 1 within the 1 milliseconds. And the second, you know that multipass is a notorious and killer factors imposing on the wireless communication. And we conduct experiment with and without the multipass effect. As a result, we can see that multipass effect indeed distorts our result, our vibration signal. However, the identified period result is the same. This evaluation shows that our algorithm is immune to the multipass effect. And in fact, the multipass help us to identify the period because it breaks the symmetry. And next, I present two case studies. The first study is to measure the window speed. The window speed can be measured to use this tool like this. This tool is composed of the 3 cups. And it's also wired connected to a meter. The meter supplies the energy and connects the signals from the cups. And in our experiment, we attach an RFID tag on one of the cups, and inspect the vibration. And we can see that we can get almost the same result as that use the specialized device sensors. And the second, as shown in our demo, we show how to monitor the centrifugation. We let the tag conduct the spinning at the frequency of the 6,000 RPM. And this figure shows the result of recovered signal. And we also use our system to track the time of the centrifugation, and the mean time error is around 1 second. Okay, in summary, in this work, we supplement a new sensing function to the backscatter signals, and we implement our systems purely based on the latest RFID systems. Thank you.